Hello there, Year 9 and 10. Welcome back to another online lesson from St Leonard's Academy Science Department Physics. We are now, incredibly enough, onto our 9th online lesson. So that's 9 weeks of lockdown, more than 9 weeks, of course, because we didn't offer them at the start, but we've been doing these online lessons for 9 weeks. So very well done. If you've made it this far, still going with the online lessons, I've seen some fantastic work submitted for the last lesson that we did. This is the last full lesson in the set of online lessons. Next week, I will put up a quick revision lesson to just going over all of the different topics that we touched on. And I'll also put up a quick test, kind of mock paper 1 test for you to do, which you can submit and I'll get marked and back to you by the following week, so that you have something which you've got something to show for all of the fantastic work that you've been doing throughout the term with the online lessons. Okay, so without further ado, let's get on with this week's lesson. It's online lesson 9, and we're looking this lesson at CP5, which is electromagnetic waves. What is an electromagnetic wave, and what is the electromagnetic spectrum? Those are the questions we'll be trying to answer this lesson. I'm going to keep it to much less than an hour this time. I know that some of my lessons were quite long, but this time it'll be a lot shorter, I promise. The equipment, things that you'll need, are a pen, a paper, and ideally a quiet, clear workspace. If you don't have any of those things, can you please pause the video and get them now? Thank you very much. Okay, let's move on. One other thing that may help you for this lesson is a ruler. So if you have a ruler, then that'll be helpful. Okay. Technical problems, there we go. Just the same work expectations that we've had every week. We would like you, from St Leonard's Academy Science Department, would like you to try to complete 3 hours of science work per week. And that can be in the revision booklets that we've given out. It can be on the online lessons, such as this one, or it can be your own work, for example, using BBC Bitesize or Oak National Academy. Okay. The electromagnetic spectrum. What I'd like you to do, this is a little bit of thinking outside the box for some of these images, but quickly on your page, on an A4 page, if you could write down what each of these images is of. So what is the image? What might it represent, or what could we use it to represent? And how could they all link together? And it's probably got something to do with the LQ, let's face it. So just to get you started off, I think the most difficult one is probably going to be our little firefox with all the multicolored tails. But have a think about it, link it to the other ones. But to get us started off, yeah, so this is a microwave. I hope you can all see that down here. How does the microwave heat up the food? What does it use? Okay, so I'm going to ask you in a second to pause the video and to complete that for all 5 images. So what is the image? You could draw a little piece of the image. You could draw the image out very quickly. What might it represent? What might it use to work? And how might they all link together? Just a very quick mind map. It shouldn't take you more than 2 minutes. Okay, I'd like you to pause the video now and to complete that. Okay, let's go through. Let's go through the images. So, you may well have other ideas than this. If you did, fantastic. But the things I wanted us to get, let's start with the easy, shall we? So what's this down here to the left? It is an X-ray image of someone's hand. Quite a strange one, because it looks like they've got an extra little finger sticking out. So that could be as a result of a deformity from birth, so a birth deformity. How do we get X-ray images? It is by using X-rays. So it's an X-ray image taken using X-rays. Our microwave, down at the bottom here. How do microwaves heat up the food? The clue is in the name. They use something called a microwave. As is the clue in the name of microwave, a microwave is a type of wave, as is an X-ray. Our torch then, to the left. How do torches work? What might it represent? Torches operate using visible light. They emit, that is, they give out visible light. Visible light is also a wave. It's a wave phenomena. So there are three. Now, this one I appreciate could be a bit confusing because you could think of it as a speaker and say that it gives out sound waves, sound energy. But I wanted us to think a bit more broadly. It is a radio. How do radios work? What kind of wave do they use? And yes, they emit sound waves, but they take in radio waves. Okay, radio waves are another kind of wave. And then finally, our Firefox, the top left. It has a rainbow-coloured tail, or many tails, forming the colours of the rainbow, missing out one of the 7. I wanted this to represent a rainbow. And why do rainbows form? Well, what are rainbows? If you put a rainbow all together, if you were to superimpose all of those colours over on top of each other, you would get white light. If I split white light apart from it, if I split white light, it is made up of all of the different colours of the rainbow. So we can think of this fox with the different coloured tails as representing a rainbow, which itself represents visible light. What are the colours of the rainbow? What do the colours represent? We're going to find out later on in the lesson. But the answer, to give it away, is that they represent, the different colours of the rainbow represent different wavelengths or different frequencies of the visible light part of the spectrum. And what's the link linking all of these together? Hopefully you got it. They are all waves in the electromagnetic spectrum. So all of these waves, microwaves, X-rays, visible light, radio waves, are electromagnetic waves. Each one operates with a different part of the electromagnetic spectrum. Don't worry if I'm speaking, it's like I'm speaking in a foreign language. We're going to go into what is an electromagnetic wave, and we're going to have a look at what is the electromagnetic spectrum. That was just to get you thinking, to get you started. And to know, and to see, just to go back, and to see how critical electromagnetic waves are to our daily life. I have included an example later on of a mobile phone. Mobile phones wouldn't work without electromagnetic waves. So electromagnetic waves really are, they form such an important part of almost everything that we do. Without visible light, we wouldn't be able to see anything without that part of the spectrum. Our eyes are special sense organs which have evolved over millions and millions of years to pick up, to detect the visible light part of the electromagnetic spectrum. Okay. This, sorry, that's not a very well put together slide. It should say electromagnetic wave, EM wave, animation. So, as with all waves, an electromagnetic wave transfers energy as radiation from a source of the waves to an absorber. They transfer energy and not mass. They also transfer information. So energy and information, not mass. Here's my torch. Visible light is an electromagnetic wave. So I turn on my torch, and it emits a beam of visible light. That's my visible light, represented as a trapezium. Now we can't see the individual rays of light, but if we could zoom in very, very finely and see the actual rays, the individual rays or the individual photons of light, we would see something like this. This is like we've zoomed in. You can almost imagine that we've zoomed in very, 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 very close to the light rays, the light beams, which are passing out of the light. What can we see? We've got two fields. We've got vibrations or oscillations in two fields at right angles to each other. I know that's quite confusing, but don't worry about it. We don't need to know too much about the oscillation or the vibration of these two fields. We just need to know that, as the name suggests, electromagnetic waves, these two fields are oscillations in the electric field, and the magnetic field. The magnetic field is indicated by this red arrow and the red wave, and the electric field here is indicated by the blue wave. So the waves are at right angles to each other. So it's this 90 degrees to each other, and they are also at 90 degrees that the wave is moving in. So this wave is coming out of the torch and coming away from the torch. But the oscillations or the vibrations in the electric and the magnetic field are at right angles to each other and to the direction of wave movement or propagation. Okay, here's another model or image of a wave traveling, or a light ray traveling, an electromagnetic wave, traveling forwards. Okay. Last lesson, we looked at transverse and longitudinal waves. In transverse waves, the oscillation or the vibration of the wave is at right angles to the direction of wave travel. In longitudinal waves, the vibration is along the direction, parallel to the direction of wave travel. In an electromagnetic wave, like this one pictured, the oscillation, as we saw in the previous slide, is at right angles to the direction of wave travel. So, electromagnetic waves are transverse waves. Their vibrations or oscillations are at changes in the electrical and magnetic fields at right angles to the direction of wave travel. And as it says at the bottom, all electromagnetic waves travel at the same speed in a vacuum, 3 times 10 to the 8 meters per second. That is 3 followed by 8 zeros. Okay, I would like you to take a quick note of that, because that's going to be important. Just that electromagnetic waves are transverse waves, and that their vibrations are changes in electrical and magnetic fields at right angles to the direction of wave travel. It will also help you to draw out, or attempt to draw out, I know it's quite difficult, but if you attempt to draw this model of an electromagnetic wave, marking the magnetic field, the electric field, the propagation direction, that just means the movement, the direction of travel of the wave. And you can also add in the wavelength, which is the length or distance between two crests. And also write down the speed of light, the speed of electromagnetic waves in a vacuum. They all travel at the same speed, 3 times 10 to the 8 meters per second. That is the speed of light. Okay, now there are two more terms that we need to know about for waves to help us to describe the different kinds of electromagnetic waves. As you can see in our picture of the wave, in our model of this wave, we have the wavelength drawn on. And the wavelength of an electromagnetic wave is the distance from one crest to another. So you can pick either the oscillation in the magnetic field, or you can pick the oscillation in the electric field and measure the distance. Wavelength is simply the measured distance between the crest in one field and the crest in the next crest in the same field. It would also work if we used a trough. The frequency of an electromagnetic wave is if I position myself at one point, say for example here, and I had a wave coming towards me in this direction, is how many wave crests pass me in 1 second. This is the same, these two words, wavelength and frequency, are the same for all waves. We can use those for sound waves, we can use them for water waves, we can use them for electromagnetic waves. These two words are fundamental for understanding different waves, wavelength and frequency. So if I stood and I counted, if I stood on a dock next to some water waves hitting against the dock, and I counted that 3 water waves hit the dock every second, then the frequency would be 3 hertz. So wavelength is measured in meters and frequency is measured in hertz, which is the same as 1 over a second, every second. You can think of it as every second. So if the frequency is 3, then it's 3 waves every second. Okay, I would like you to copy down the red box, as we always do. What is a wavelength and what is the frequency of a wave? Excellent. Now, for a bit of practice. I've told you what wavelength and frequency are. Here we have a GIF of a wave, the same GIF we saw before, of an electromagnetic wave. I'd like you to try to estimate the wavelength and the frequency of this wave. How are we going to do it? Don't worry, I'll help you out. How we can do it is to pick a point. I suggest we pick the end here where we can see the arrows. Estimate the wavelength is going to be simple. Well, not simple because you haven't done it before, but we estimate how many crests, if we have 100 meters here, how many full wave 100 meters. We can divide that by the number of waves, and that will give us the length of one wave. So we've got a scale of 100 meters from this end to this end. And if we count the crests, let's just pick one field. So I'm going to pick the electric field because that's the one that's most prominent. I'm going to count these crests here as they pass approximately. How many are there from one end of this graph to another? I think we have about 4. At any point, we have 4 crests traveling in 100 meters. If 4 of them make up 100 meters, then the wavelength of one wave from one crest to another crest is going to be 100 divided by 4. It's going to be 25 meters. Now for the frequency, if we pick this one point again, we want to think how many waves pass in 1 second. Now, in fact, it's probably less than 1 pass in 1 second. So to make it easy, let's think about how many pass in 10 seconds. So pick this point here, and then we'll time 10 seconds, and you count how many waves pass. Okay, I'm going to time us on my phone. So timer, 10 seconds. Are you looking? I'm going to say ready, steady, go, and then start counting. We'll count how many waves pass in 10 seconds. Ready, steady, and go. and stop. So I think we had about 3 or 4 waves passing in 10 seconds. If 4 waves, that's 4 wave crests passed in that time. If 4 waves pass in 10 seconds, we do 4 divided by 10 is going to be 0.4 waves pass every second. So if 4 waves pass in 10 seconds, we want to know for the frequency how many waves pass in 1 second. Divide 4 by 10 and we get 0.4 of the frequency. The unit for frequency is hertz, which is a capital H and a small z. So the frequency of this wave is going to be 0.4 hertz, and the wavelength, as we worked out, is going to be 25 meters. Okay, let's move on. I appreciate that's all quite heavy, and it'll help you, if you practice a few questions at it, it will help you to understand those two terms, frequency and wavelength. I'll put some links below if you want to do some practice questions. This slide, this is pretty much our last slide of content. There's a lot of information there, for which I don't apologize, because if you get this information, if you get this diagram, then you basically understand everything there is to know about the electromagnetic spectrum. Okay, not quite, but most of it. What is the electromagnetic spectrum? So if we thought of, if we put all of the different kinds of electromagnetic waves that we could get in order of their frequency, or in order of their wavelength, then we would get the, so from longer wavelength to shorter wavelength, from lower frequency to higher frequency, then we would get the electromagnetic spectrum. Why do we have these different names for the different parts of the spectrum? It's because they have very different properties. Waves of a certain wavelength have certain properties, and as that wavelength increases or decreases, eventually those waves start to have very different properties. So for example, you can see the visible part of the electromagnetic spectrum has a wavelength in centimeters of about 10 to the minus 5. That's the same order of magnitude as about the size of a bacteria or a protozoan, as shown. Visible light is the electromagnetic wave, a part of the electromagnetic spectrum that we can pick up with our eyes. Other parts of the spectrum, in order then, from the lowest frequency or the largest wavelength, is radio, then microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. Underneath, we've got the wavelength in centimeters, and we've got pictures of what is that wavelength about the size of, roughly the size of. If you could please copy down this diagram exactly, well, roughly as it is in your book, leaving some space below it because we're going to add frequency and energy onto our diagram. And once you've got this diagram, we're going to use it then later on in the lesson to help you out with getting the different parts of the spectrum. So just a little bit more description of the different parts before you copy that down. What different types of things produce these, or do we use them for? So radio waves, we use radio waves for mobile phones. We use them for radios, of course. Your mobile phone emits radio waves which go to the mobile phone mast when you make a call, and it also receives the radio waves into itself, so that you can then hear someone else or receive information. Microwaves, we use those for some kinds of communication, for radar, and also, of course, for microwave cookers. Infrared is part of the electromagnetic spectrum which is emitted by hot bodies of temperatures up to a few hundred degrees centigrade. We use it in TV remotes, emit infrared radiation, and it's emitted by things like fires and hot objects up to a certain temperature. Visible light is emitted by light bulbs, and we use it to see with. Ultraviolet is emitted by the sun. It's the part of the spectrum which gives us a suntan, so it's a higher energy part than visible. X-rays are emitted by X-ray machines, and gamma which we use for X-raying our bones, and gamma rays are emitted by unstable radioactive nuclei. Okay, so how do we remember? We need to remember what all of the different waves are and what order they're in. How we usually do that in school is to use a mnemonic. Now you can come up with your own, or you can write below or above your diagram the one that I've come up with here. Rebel monkeys in velvet underpants excrete gummy bears. So include that above or below your diagram. I'm going to ask you to pause the video now and to write and to draw out the diagram as it is here. Okay, you can pause the video now. Okay, fantastic. Now there's just a couple more things we need to add, and then I promise we've got all the information that we need for the rest of this lesson. So one thing, you can see it in the wavelength, in the numbers for the wavelength, but one thing to make it really clear is that our spectrum is all of the different electromagnetic waves that there could be in order of wavelength, going from long wavelength, radio, to short wavelength, gamma ray. So microwave is shorter, infrared shorter, visible shorter, ultraviolet, X-ray shorter still, until gamma ray is the shortest wavelength. Frequency and energy of waves is the opposite. So it goes from low frequency at the radio end, so few waves passed per second, to high frequency at the gamma ray end of the electromagnetic spectrum. We can think of that as that wavelength and frequency increase in inverse or opposite directions. So wavelength increases as we go from gamma ray to radio, and frequency increases as we go from radio to gamma ray, the other way around. Can you add those two to your diagram, please? Thank you very much. If you haven't added them, then pause the video and add those above or below your diagram of the electromagnetic spectrum. So what is the electromagnetic spectrum? If you're asked that as a question, it is all of the waves, all of the electromagnetic waves which exist ordered in terms of ordered by their wavelength from long to short, or by their frequency from low to high. Okay, now it's time for you guys to try some questions. I'd like you to try to choose which part of the electromagnetic spectrum is used for these different things. So which part do we use for looking at broken bones? Which part can be split into different colours of the rainbow? Which part can be used for cooking food? Which part are very dangerous rays given off by radioactive substances? Those are the highest energy ones. That's why they're dangerous. As a clue. Number 5, which part is given off by hot objects? Number 6, which part of the spectrum gives you a suntan but can also cause cancer? Number 7, which part is used for TV and radio communication? And number 8, which has the shortest wavelength? Number 9, which part of the spectrum has the lowest frequency? If you're unsure of these, you can flick back to the diagram you've just copied out. It should help you out. Okay, I'd like you to pause the video and give that a go. Try to answer all of them. Just give them a guess, even if you don't know for certain. Okay, you can pause the video now. Okay, what are the answers? Used to look at broken bones, X-rays. What can be split into the colours of the rainbow? That's visible light. What can be used for cooking food? Microwaves. Very dangerous, given off by radioactive substances, is gamma rays. What's given off by hot objects? That is infrared. What gives you a suntan but can cause cancer? Ultraviolet. Which part is used for TV and radio communication? That is radio waves. Which have the shortest wavelength? Gamma rays, gamma waves, gamma rays. Which have the lowest frequency? That is radio waves. Okay, quick quiz, continue. Quick quiz part 2, shall we say? Have a go at these. Which part has the longest wavelength? Which part has the highest frequency? Which part is in the middle of the spectrum if you order them from left to right? What begins with a U, and what is 6th in the spectrum going from radio one side across? Okay, pause the video and give this a go. Okay, let's go through the answers. Give yourself a mark out of 5. It is radio waves. Number 1 has the longest wavelength. Which has the highest frequency? It is 2, gamma. Which one is in the middle of the spectrum? That's visible light. Which one begins with the letter U? That's ultraviolet. And what's 6th in the spectrum? X-rays. So there are 7 different parts. Okay, now I want you to have a go at completing this table. So you're going to have to draw this table out, go on to the next full page of your book. You're going to need 1, 2, 3, 4, 5, 6, 7, 8 rows, and 1, 2, 3, 4, 5, 6, 7, 8 columns. For higher students, higher or triple students, have a go at the bottom ones in purple. You might need to research. In fact, don't worry about temperature of an object emitting, because we haven't done that. That was in the previous in the lesson, as we did if we did it non-virtually. And for whether they penetrate the atmosphere, you'll need to research that yourself. Okay, so you might like to use your phone to see whether this part of the spectrum emits this or can penetrate Earth's atmosphere. Okay, so what we're looking for is which is the part of the spectrum. We start at radio waves, and then we go through the spectrum, going shorter wavelengths. If you're struggling, think of the mnemonic, which was rebel monkeys in velvet underpants excrete gummy bears. That should help you out. And then wavelength. We start at long, and then we get shorter, fill it in until we get to short. Frequency, we start low. Wavelengths have low frequency, and then they get higher and higher until we get to high frequency at the end. Wave diagram, we've got that drawn out already. This is just to show you that the wavelengths are decreasing as we go down the spectrum. What's the equivalent size? So have a look at the diagram that you drew out for the previous slide where we drew out the spectrum. What's the equivalent size? Have a go. Think if you can think of a source for each one. And do they penetrate the atmosphere? Don't worry about the temperature of an object. Okay, pause the video and try to fill in the table. I'd like you to pause the video now. Okay, let's go through the answers. I'd like you to write in the correct answer if you didn't get it. You may have other answers, but I'd like you to write these ones in. So I didn't include the temperature because I thought that was a bit too much, a bit too confusing. We go radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. Wavelength. Now these do have a actual. We have a set wavelength in meters for radio waves, but I didn't want to go into that much detail, so I just changed it for long. Long, shorter, until we get to short for gamma rays. Frequency is low for radio waves, and it goes higher until we get to high for gamma rays. The equivalent size of these, so you could have copied the ones out from the previous diagram, or if you've got something like this: football pitch, baseball, a pinhead or a cell, bacteria, be a human cell, bacteria, virus, protein, and atomic nuclei. And then where do they come from, the different parts of the spectrum? What are the sources? There are other sources: AM, FM radio for radio waves, microwave, people for infrared, light bulbs for visible, the sun for ultraviolet, X-ray machines for X-ray, radioactive materials for gamma rays. And then do they penetrate the atmosphere? Yes, some, yes, some near ultraviolet, no. And do gamma rays penetrate the atmosphere? Let's find out. When I move, no, gamma rays don't. Okay, very well done. Take a picture of it and submit it to Shobi, or send it as an email to me at d.devlin@hasler.org.uk, and you'll be notified in the newsletter which goes out each week if you got it all correct. So I'm relying on you being honest. Okay, final quiz, and then we'll go to our exit ticket. So this is complete the sentences by choosing the correct word. You can just write 1, 2, 3, 4, 5, 6, 7, 8, 9. You don't have to copy out the full text, but complete by choosing the right word. All electromagnetic waves are what kind of waves? And like other waves, blah, 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 so on and so forth. Okay, I'd like to pause the video and give that a go now. Okay, let's go through. All electromagnetic waves are transverse waves. And like other waves, they transfer energy, not matter. They all travel at 3 times 10 to the 8 meters per second in a vacuum. Vacuum means there's no gas or air particles. So space, for example, is a vacuum. This is known as the speed of light. Electromagnetic waves travel at different speeds in different materials. And as with other waves, are refracted as they move between mediums at an interface. Don't worry about that last sentence. So we haven't really dealt with that, okay? So if you didn't get those ones, don't worry too much. If you did, very well done. Okay. And that's us. That's us done for electromagnetic waves. If you found that to be confusing, don't worry, because it is a confusing topic. I will include a link to the BBC Bitesize topic for electromagnetic waves, the revision material for electromagnetic waves, which if you're completely stuck and you can't do any of the exit ticket questions, you might like to go over to help you understand. The exit ticket, try to match the diagrams to the type of wave the object produces. We have a loudspeaker, a TV remote, a sunbed, a mobile phone connecting to a phone tower. And these are the types of waves: sound, ultraviolet, radio, and infrared. I'm so kind, I've done one for you. Phones connecting to mobile phones connecting to the mobile phone mast, it uses radio waves. So what do loudspeakers, TV remotes, and sunbeds use? Question 2, which one of the waves is not in the electromagnetic spectrum? Question 3, which one of the waves has a wavelength shorter than light? Only one of them. That's visible light. And we've got a couple more. Number 4, describe an electromagnetic wave. And that's for 3 marks. Hint, it's 3 marks, so we're looking for 3 points. The ones I would go for: what is a wave? What type of wave is an electromagnetic wave? And what are the vibrations in an electromagnetic wave? The clue is in the name. And number 5, that's 3 marks. Number 5, compare the wavelength of an X-ray to that of a water wave at the beach. Which one's higher? Which one's lower? And if you like, you could find out the typical wavelength of an X-ray and of a water wave. Okay, that's us. All done. Was that less than an hour? Yes, a lot less than an hour. So submit your answers to showbie.com, class code HZ9N9, by Tuesday the 7th of July at 12:05 p.m. to get it marked by a teacher at St Leonard's Academy. Spoiler, it's probably going to be me that marks it. Okay, looking forward to getting your answers. As I said, that's the end of the taught material. We'll have a revision lesson next week, and I'll set you a little mock paper. Yay! It's been a real pleasure. I won't say goodbye yet because it's not the end. It's not my last online lesson. Okay, good luck with that, and I'll see you next week. Mr. Devlin out.